Hello ladies and gentlemen, so welcome back to the video on uniform motion. So we're going to continue with the notes and problems, and let's look at what we're going to do first. All right, we're going to move on to examples on motion diagrams. So we're going to look at the graphical interpretation of motion diagrams. So we'll start with the instantaneous velocity. This is the first point about motion diagrams. When you're looking at diagrams involving motion, the instantaneous velocity of an object at a certain time is the slope of the displacement versus time graph. So the instantaneous velocity is just the slope of the displacement versus the velocity time graph at that time. It can be positive, negative, or zero. So what do we mean by instantaneous velocity? Instantaneous velocity is just the velocity at that instant. Okay, or the limit of delta x over delta t as delta t approaches 0. Okay, so it's just the velocity of an object at a particular time. Yeah, there are many definitions of instantaneous velocity. So the velocity at an instant of time, it can be called instantaneous velocity. Or to be explicit, you can say the limit of delta x over delta t as delta t approaches 0. That is instantaneous velocity, where delta x is the displacement, the change in displacement, and delta t is the change in time. All right, and the instantaneous acceleration of an object at a certain time is just the slope of the graph, or rather the slope of the velocity against time graph. That is the instantaneous acceleration, the slope of the velocity against time graph. So here there was that part missing here. I missed a part here. It should say the instantaneous acceleration of an object at a certain time is just the slope of the velocity against time graph at that time. Okay, that's the slope. Okay, and all right, so that is instantaneous velocity and acceleration. And here, when you look at the slope is just gradient. That is something which you know. Slope is just representing the gradient of that graph. A slope is a gradient, and all of you know how to calculate for the gradient. So if you're here, you must know how to calculate for the gradient of a slope. Okay, so whether the slope is a curve or a straight line, you have to know how to solve for the gradient. Yes, and the procedure for solving for the gradient is the same procedure you are using when in grade 12 mathematics. You are solving for the gradient of a curve by making a tangent at a certain point of a curve, then solving for the change in y and the change in x. That was the gradient. So it's the same principle we'll be applying. So let's look at an example 1 where we have an object's one-dimensional motion along the x-axis is graphed in figure 2.2. So an object's one-dimensional motion along the x-axis is graphed in figure 2.2. So this is our figure 2.2 apparently. Describe its motion. So I want to describe the motion of this object. So what you have is a displacement versus time graph. So if you find the gradient of a displacement versus time graph, when you look at what you have here, we're saying the instantaneous velocity of an object at a certain time is the slope of the displacement versus time graph, which we have here. So we have a displacement versus time graph here. So we have an object's one-dimensional motion along the x-axis is graphed here. So we have displacement against time. So I want to describe this motion using what we have in this diagram. So now when you look at this diagram, we have an object starting from 0. Okay, it was at rest here because it had no change in displacement between this point and this point. There was no change in displacement. Okay, and when you look at this line, it's a straight line. How do you find the gradient of a straight line? I mean, this is a horizontal line. The gradient of a horizontal line is always 0. Why? Because the change in y is 0. The gradient of a horizontal line is 0. So between time 0 and time 2. So when you look at the partition between this point 0 and this point, this must be 2. This must be 4. This must be 6. This must be 8. This must be 10. This must be 12. Okay. So now, from t equals 0 to t equals 2, the slope is 0. Okay. Because we have a straight line. Okay. It's a straight line and it is a horizontal line. It is a horizontal line. The gradient is 0. Hence the velocity is 0. When you find the gradient of this line, you find that it will be 0. And you all know how to find the gradient. We always find it by taking the change in y, this is the y axis, minus the change in the x axis, which is this axis where there is a time. So this is the time axis. Change in displacement axis minus change in time axis, which is the same as change in y minus change in x. So now we have a straight line, velocity is 0. So we've described from t equals 0 to t equals 2. Now let's describe from t equals 2 to t equals 4. So when you look at this graph again, from t equals 2 here to t equals 4, what is the slope of this line? Okay, what is the slope of this line? So the slope of this line is just the change in the vertical axis minus the change in the horizontal axis. So the change in the vertical axis is from this point to this point, which is same as from this point going all the way to that point. So it's from this point to that point, which is just, if this is 0, this must be 1, this must be 2, this must be 3, and this is 4 as shown. So now this is from initial point 0 to final point 3. So change in y will be, it will just be 3 minus 0 over change in x. Change in x is just 4 minus 2, right? Because when you look at this slope, it's just 4 minus 2. That's the change in x. So that's what you have, 3 minus 0 over 4 minus 2, which is given 1.5 meters per second is the velocity between t equals 2 and t equals 4. Now from t equals 4 to t equals 6, what is happening? From t equals 4 to t equals 6 here, as you can see, this is a horizontal line. This is a horizontal line, mean that gradient is also 0, mean that velocity is 0. So velocity is 0. Yeah. From t equals 4 to t equals 6, slope is 0. Velocity is 0. Car is not moving. So yeah, the car is not moving because velocity is 0, right? Now from t equals 6 to t equals 10, we have, let's say, t equals 6 to 10, t equals 6. Wait, where am I? Where are you? From t equals, yeah. Now this other part of the graph, going all the way down to whatever point it is going at. So for this part of the graph, we can't take this point as reference to solving for the gradient because this is not exactly passing on 8. This line is not passing on time because 8 exactly. It is after this 8, but using what you've been given these dotted lines which are showing you the exact location of some point. There's a point there and there's a point here. So you can use this point and this point to solve for the gradient. Okay, you can use this point and this point to solve for the gradient, or any point along any 2 points which you are sure of along this line can work to solve for the gradient. Any 2 points along this line can work to solve for the gradient. So it's just change in y must change in x. So change in y is just from this point to this point. I mean rather from this point to this point. Since this must now be the initial, this must be the final, because the graph is going like that, like that, like that, and then like that. So this must be the initial, final. So this is minus 2, minus 3. So negative 2 minus 3, that's the change in y, minus change in x, which is from this point to this point. So the change in x is just 10 minus 6. Okay, so yeah, this is what we have. Negative 2 minus 3 divided by 10 minus 6, which gives minus 1.3 meters per second. So between time t equals 6 to t equals 10, this object is moving with this velocity of negative 1.3 meters per second. Okay, it's moving with that velocity. Alright, so now we can even move on to projectile motion. So projectile motion, this is something we've all been observing every time when people are playing golf, okay, or someone is playing basketball. We observe projectile motion, which is just motion in 2 dimensions. So anyone who has observed a baseball or a basketball in motion has observed projectile motion. Okay, the ball moves in a curved path. Of course, when you throw a ball, it will move in a curved path and returns to the ground. We analyze projectile motion by making these assumptions. 1. The free fall acceleration is constant and directed downwards. So the free fall acceleration, which is gravity, is constant and always downwards directed. The second assumption is the effects of air resistance is negligible. So we don't consider air resistance when we're solving for projectile motion. Air resistance is negligible. Now, using these assumptions, we find that the path of a projectile, which we call its trajectory, is always a parabola. So it's a parabola, that is a path of a projectile, and that path is called a trajectory. Okay, so this is what we have as the assumption. This is what we have as the assumptions. So you can even define projectile motion as the motion of an object in 2 dimensions as it moves in a parabolic manner. Okay, it's the motion of an object in 2 dimensions in a parabolic manner. So an object moving in a parabola in 2 dimensions is a projectile, and it's undergoing projectile motion. And the effects of air resistance are neglected, of course. So this is an example of a diagram showing you projectile motion. You have an axis x, y axis, and an object with theta here, and initial velocity v subscript I. So the distance from O to some point X here is just R, the range of a projectile. So the horizontal distance is called the range of a projectile, and from this point to that point, representing the maximum height of a projectile. So this is figure A. So from figure above, Vi is the initial velocity. So V subscript I is the initial velocity. The x and y components of initial velocity are Vxi and Vyi respectively. Okay. Now these are Vix or Xi. However you can put it, whether you start with x then I or I with x, I don't mind as long as it is shown. Alright, so Vix is equal to Vi cos theta. Vix is equal to Vi cos theta. Vi is the initial velocity, cos theta the angle. This is how we get the components of velocity in the x-axis. This is the component of velocity in the x-axis, which is Vix, the component of velocity in the x-axis here. You get this by just formulating a triangle here on this vector. You find that this part will have a component of Vi cos theta, and this part will just have a Vi sin theta. That is what you have as the y component is just Vi sin theta. Alright, so this is the y component of velocity. Vyi is equal to Vi sin theta. That's the y component of velocity. Alright, yeah. So we get the y component, but also same thing, making a triangle on this vector coming down there. If you form up a triangle there, you find that the vertical axis will have a magnitude of Vi cos theta from this initial velocity. Okay, that's the y component of velocity. And projectile motion can be analyzed as a combination of two independent motions in the x and y direction. So it can be analyzed as a combination of two independent motions in the x and y direction, A subscript x and A subscript y. However, projectile motion can be handled zero acceleration in the x direction. Okay, that's how it is. The x component of acceleration is always zero whenever you're dealing with projectile motion. Okay, the horizontal component of acceleration is always zero, which is the same as the x direction. X direction, the acceleration is zero. And the constant acceleration in the y direction, which is A subscript y. In the y direction, we have a constant acceleration, which is equal to the gravity, which is A subscript y is equal to the gravity, which is minus g. This minus comes in because we choose up as positive in most cases. We choose up as positive, but gravity is always downwards directed. That's why there is a minus here. Okay, now let's look at the horizontal range and maximum height of a particle undergoing projectile motion. Horizontal range and maximum height of a particle. Now to get the maximum height, we first find the time taken to reach max height at point A. Okay, to get maximum height, we first find the time taken to reach max height at point A. Of course, point A is just here. In this same diagram, figure A, there's point A. We must find the time taken to reach this point A. Okay, so now let's see what we have. Yes, to get the maximum height, we first find the time taken to reach max height at point A in figure A. Now at point A, the y component of final velocity, okay, vyf. So this is v subscript yf here. I know it's not clear, but this is v subscript yf. So I'll repeat, at final point A, okay, and the final point A is just a maximum height, as you can see. The y component of final velocity will be 0, okay, because the y component of that motion will be 0 because it will be at rest. The y component of velocity will be 0 because that particle will become momentarily at rest when you consider the y component. That's why I was saying that at A, the y component of final velocity will be 0. What do we mean? What we mean is Vy final. So remember, right now we're solving for the maximum height, the time to reach maximum height. So we're saying Vy final is equal to Viy plus At. Remember, we're dealing with the y component here. We are dealing with the y component. That's something you should note. This is us dealing with the y component first to find the maximum height. To find the time to reach maximum height. So now, final velocity in the y must be 0 because vertically, that particle should come momentarily at rest. When we consider the y component, it will be 0 is equal to Viy, V subscript Iy. Now, Viy must just be the initial velocity in the vertical axis. So initial velocity in the y-axis, that is Viy initial in the y-axis, must be equal to Vi sine theta, okay, plus Ay. Now, acceleration in the vertical axis is just gravity, which is negative g, which is the minus g, times the t here, which is the time. So remember, I said Viy here is just the component of velocity in the y-axis, the initial component of velocity in the y-axis, which is what we wrote here. Vyi or Viy is the same thing. I don't mind whether I write V subscript Iy or V subscript Yi, which is just Vi sine theta. Alright, moving on. From here we can even make t the subject to the formula now. Making time the subject to the formula, I have t is equal to Vi sine theta. You have to make this cross to the other side. We get Vi sine theta over g. Okay. Now, T subscript A, this is implying time at A is equal to Vi sine theta over g as time to reach the maximum height at A. So now, how do we get the maximum height from the time to reach maximum height? So get maximum height by substituting for this time in our equation for displacement, which is this. This is an equation for displacement, which is y is equal to V subscript Iyt plus half Ayt squared. So I'm using y because now I'm dealing with the vertical motion, which is the y-axis. Well, that's what we want to find. Maximum height is in the y-axis. That's why we're dealing with y here. So y is equal to Viyt plus half Ayt squared. Okay. So now, what do we have here? H, which is y, our height, must be equal to Viy now. This is initial velocity in the y-axis, which is just that component of velocity, which is Vi sine theta. So Vi sine theta is Viy times time. This is the time now to reach maximum height, which we found here as t at A. Point A is the maximum height, which is what we've substituted for time in this part of the equation, and we're getting this expression like that. plus half a subscript y is just negative g, which is gravity, which is plus half minus g. Okay, now t squared is just this time again comes back here and it gets this position, then we square it. Okay, so now what is this times this? This is just you see there's a vi here and there's a vi here. When we multiply, they will become vi squared. There's sine theta and there's sine theta to become sine squared theta over this same g, plus now there is a half here, of course, which has come back here as a 2 in the denominator. Now there's a g there and there's a g there, but this g is squared, so we only remain with 1g. After this one cancels out, we remain with 1g as it is there, and vi is squared, that's why it is here squared. Sine theta is squared, that's why it is squared here. Now this minus this is this. Okay, vi squared sine squared theta minus vi squared sine squared theta over 2g is this expression. So when you subtract this minus this, we're getting this as the maximum height. So the maximum height is v subscript I squared sine squared theta over 2g. That's our maximum height. Now, the range R is the horizontal position. Okay, so the range is the horizontal position of a projectile at a time that is twice the time to reach the peak at A. So what do we mean? What do we mean here? What we just mean is that to get the horizontal range, we must take the time which is twice the time to reach at point A. We must take the time which is twice the time to reach at point A. So whatever time we found at point A, we must make it twice. Okay, we must multiply it by 2 if we want to find the horizontal range, or if we want to find the time or the displacement for the horizontal range. You must use that time, which is twice the time at A. So when we look at one of the equations of uniform motion for displacement is just x. Now you see it has now changed to x because we're looking at the horizontal distance, or the horizontal displacement rather. We're looking at the horizontal displacement, that's why we're using now x. X is the horizontal axis, which is r, the range, which is equal to v I. Okay, so you see this was a mistake. This should be v I x t, not y here. I'll repeat. Since we're looking at the range, the horizontal range r, this must be v subscript I x, not this one. It shouldn't be. It shouldn't be this. Yeah, it shouldn't be this. This is wrong. So it should be like yeah, this should be, yeah, let me just remove this. So this should be v subscript I yes, just do this. Okay, so let me just write the correct stuff here. V subscript I x, not y. So this must be I x. Yeah, this must be like that. This is I. Okay. Yeah, it's looking a bit messy now. Okay, so this is what you have. X equals V subscript I x times time plus half A subscript x t squared. So now when you look at this, an equation of uniform motion, we use this equation for the range, but A subscript x is 0. This is just acceleration in the horizontal axis is 0, as we saw in the notes. Acceleration is 0 in the x-axis. That's why I was saying a subscript xt, but ax is 0. So if this is 0, we just remain with it. Yeah. So this thing has repeated. This thing has repeated itself. So this is let's just get rid of this to avoid confusion. Yeah, let's just do that. Okay, let's just make it better. Yeah, we subscript ix. So this is what I'm not trying to correct this. Okay, so r is equal to vi subscript ix times time. So only getting this because this part will become 0. So but t is now twice the time to reach at point A. That is t is equal to 2ta. So yeah, this should be 2ta. Okay, let's just do that. So this t must be equal to 2ta, twice ta, like that. Yeah, twice ta. Oh, my t is not looking good enough, but let's do this and we can do it again. Yeah, I'm trying to do a better job here. I want this t to be good. Okay, so we want it like that and a little bit like that, and let's see what we'll do. This should be a 2. Yeah, that's better. So here I was saying that but t is now twice the time to reach at point A. That is t is equal to 2ta. Hence r out of the range, we substitute for what we know. Vi subscript x just vi cos theta. Now t now is just twice t at A. Now we know what t at A is. T at A is just this. Now multiplying it by 2 is our time, which is that. I multiplied it by 2. This is why the 2 is in front there. 2vi sin theta over g. So when you multiply this by that, you get in this expression. You're getting 2vi squared sin theta cos theta. But this 2 sin theta cos theta is just an identity, a trigonometric identity, which is equal to vi squared sin 2 theta over g. So this becomes your range. All right, this is your range, horizontal range. So this applies to projectiles which are projected on a horizontal ground back to the same horizontal ground. So whatever I've just said here applies to projectiles that have been projected from the ground, and then that projectile should land on the same level. If you want to apply these formulas, it only applies to this kind of projectiles where the particle has been projected from one level ground to the same level ground. All right, so let's now try to look at something else. So now note horizontal range is maximum at theta equals 45 degrees. All right, yeah, this is the angle at which you can get the maximum range. When you project a particle at theta equals 45 degrees, that's the only way you can get a maximum range, because you get a maximum value of sine 2 theta. I mean, when you look at this equation, you find that this is constant and this is constant. The only thing which will be variable is theta here. Okay, so long as vi is kept constant and g is kept constant, the horizontal range can be maximum if we project the particle at theta equals 45 degrees. Why? Because this quantity, which is a variable, because theta is varying. Okay, we're saying that the value of sine 2 theta is maximum at 1. That is, the max value of sine 2 theta is 1. So this is a trigonometric function, and its maximum value can only be 1. Okay, and when this quantity is maximum, mean that all of this will be maximum. That's why I'm saying that the maximum range is largest when theta is 45, which only occurs at theta equals 45 degrees. All right. Now, in the next video, we're going to look at examples involving projectile motion. But for now, let's relax a bit, and I'll see you in the next video where you'll be dealing with problems involving projectile motion. All right. Thanks for joining me, and have a good time.